So now I want to talk about the last section of chapter 3, section 3.7, which is about polynomial and rational inequalities. Okay, so we're going to see what happens when we have inequalities instead of equations. First, let's talk about polynomial inequalities. So to solve a polynomial inequality, the first thing we want to do is to write it in standard form by moving all the terms to one side of the inequality, all the terms to the left side, and you need to have a 0 on the right side. Okay, so that's what you want to do first. So it should look like this. Instead of p of x equals 0, it should be less than 0, greater than, less or equal, greater or equal to 0. And then you want to find all the critical values. Find all critical values by solving the polynomial equation of x equals 0. And after that, then you plot the critical values on the number line. To divide it into test intervals. So basically you get, say, two critical values, C1, C2. The number line is from negative infinity to infinity. Put C1, C2. Then there's the interval from negative infinity to C1, C1 to C2, C2. So you label them. And you use parentheses if it's less or equal, or if it's less than or greater than, brackets if less or equal or greater or equal. Again, parentheses meaning those critical values are not part of my solution set. Brackets means those critical values are part of my solution set. And after that, you want to pick a test value from within each interval. From within each interval. If the test value is a solution, where do we plug it in? It's in the original inequality of the, because that's what we're solving, original inequality. Then the whole interval is a solution. So you pick a number here between C1 and C2. You cannot pick C1 or C2, okay, x. And you plug it into the original inequality. If it makes it true, then the whole interval is true. If it makes it false, then you cross out that interval. Okay? And then once you know which intervals are true, then this is your solution set. So you want to write your answer using interval notation. Okay. So let's look at number 8, page 316. 8, page 316, we have 2x cubed minus 18x is less than x squared minus 9. So we move everything over to the left. We want to write it in standard form. So minus x squared plus 9 is less than 0. And then we want to find the critical values by setting it equal 0. And this is exactly what we have been doing for the last few sections. Excuse me, finding zeros of polynomial functions. So we're solving a cubic equation. A lot of times we could do grouping. So if we group that, like by factoring out 2x, so it would be x squared minus 9 minus 1 x squared minus 9. That's the easiest way to solve if it factors. So it does work. So x minus 3, x plus 3, 2 minus 1. So we got three critical values, 3, -3, and 1/2. Now we plot these critical values on the number line. So we're gonna have 4 intervals. There's always one more interval than the number of critical values. 3, 1/2, and -3. And since it's strictly less than, so we're gonna use parentheses. So -∞ to -3, that's one interval. -3 to 1/2, 1/2 to 3, and then 3 to infinity. And then I want to start with the easiest one to check, which is 0, which is inside interval 2. If we put a 0 in there, 2 times 0 cubed minus 18 times 0 is less than 0 squared minus 9. 0 is less than -9, which is false. So that means this whole interval is not a solution. And again, you don't really have to check every interval. Your solution intervals will alternate as long as none of these critical values appear an even number of times, like 2 times or times. X equal 3 appear 1 time, 1 time, 1 time. If this was, say, x minus 3 squared, then x equal 3 will show up twice, multiplicity is 2, then you know they're not gonna alternate. But if each one of them has a power of 1 or 3 odd power, then you're fine to do the alternating method. So if this is false, then the before is true, after is true, and then false. So they're gonna be true, false, or false, true. They're not gonna be true, true, or false, false, okay? So the true ones are 1 and 3. We're gonna do interval notation. You always have to do that. -∞, -3, union 1/2, 3. And that would be my solution set. Okay, number 14, page 316. 4 plus 3x cubed minus 3x squared plus 3x minus 4 is less than 0. And we want to solve this inequality. So if we start, it's already in standard form. We find the critical values by setting it equal to 0. And now we have to do what we learned in 3.3, 3.4, and 3.5, finding the zeros, rational zero theorem, and all that stuff. So P over Q, P is a factor of 4, and Q is a factor of 1. So P over Q, these are the possible rational zeros, 1, 2, and 4, plus or minus. Then we put it in our calculator to see which one we should divide by first. So x to the 4 plus 3x cubed minus 3x squared plus 3x minus 4, and it looks like -4 and 1 are zeros. Let's check the table. -4, does it give me a 0? Yeah. And then 1, does it give me a 0? Yep. So that's right. So we're gonna start by dividing by 1 and make sure it's in descending order and no missing exponent. It's in descending order, no missing exponent. So 1, 3, -3, 3, -4. So 1 times 1 is 1, 3 plus 1 is 4. 4 times 1 is 4, plus -3 is 1. 1 times 1 is 1, plus 3 is 4. 1 times 4 is 4, plus -4 is 0. So this can be factored. Again, 1 is a 0, so x minus 1 is a factor. There's the other factor, remainder, constant, x squared, x cubed. It looks like from here on we could do factoring, or we could do synthetic, but factoring would be easier. Look, if we group them together, x squared, x plus 4, plus 1 times x plus 4, and you can see what I'm talking about, x plus 4, x squared plus 1, x minus 1. So the critical values are 1 and -4. this doesn't give me any real numbers. It's plus or minus I, but we can't use these, okay? They're not real numbers. So these are the critical values. Then we put them on the number line. 1, 2, 3, 4. So we're going to have an interval from negative infinity to negative 4. We're using parentheses because it's less than. It's not less or equal. So interval 1, 2, 3. Again, since each one of these appear an odd number of times, we can do the alternating method. I'm going to use 0 to plug it in. All the way there, 0, 0, 0, 0 plus negative 4. So negative 4 is less than 0, which is true. So this is true, false, false. So my solution set is the 4 to 1. So any real number you pick in this interval, it's a solution. Anything you pick outside this interval will not be a solution. So this is done with polynomial inequalities. The second part of this section is about solving rational inequalities. So from rational functions to rational inequalities. So instead of f of x equals p over q, which is rational function, we're going to do p over q is less than 0 or greater than 0 or whatever, less or equal, rational inequality. So we always have to have the inequality in standard form. So the first step is to write the inequality in standard form. Write the inequality in standard form, which means you have to have a single fraction on the left side and 0 on the right side. Okay, one fraction on the left side, 0 on the right side. One fraction, 0. One fraction, 0. Okay, once you have it in that form, then you find critical values, just like we did with polynomial inequalities. Critical values, this time we find them by setting p equals 0 and q equals 0, top and bottom. Okay, and then the rest is the same. You plot the critical values on the number line, plot on the number line to divide it into intervals. I'm not going to write everything down. Use test intervals, and then again they alternate as long as none of them show up an even number of times. But be careful because we have a denominator here, so I'll just explain that to you. Okay, it says make sure that you always have a parentheses at any critical number that produces a 0 in the denominator. That's what's new here, but I'll explain that. Okay, but everything else more or less is like polynomial inequality. So here 20, and I'll show you the difference. So how do we solve the rational inequality? 4x squared minus 25 over x squared minus 9 is less or equal to 0. So we already have 0 on this side and a single fraction on that side. It's already in standard form. To find the critical values, we're going to set 4x squared minus 25 equals 0 and x squared minus 9 equals 0. So we're solving, this is the difference of two squares, 2x minus 5, 2x plus 5. So we get two critical values, 5 over 2, and each one of them appears one time. Same thing here, plus 3, x minus 3. There's two critical values, so a total of 4 critical values, and each one of them show up an odd number of times, so they alternate. So we're going to have 5 test intervals, right? There's 4 of these. There's going to be one more interval as usual. So we're going to put them in order. 0 is right here, negative 3. There's negative 3, negative 5 over 2, and then the next one is 5 over 2, which is 2.5, and then 3. So we have the interval from negative. Now, since we have less or equal, we're supposed to use what? Brackets. The only thing is, you have to have a parentheses and at any critical number that produces a 0 in the denominator. So if you look at the denominator, this is the denominator, we got a 0 when x is negative 3 or x equals 3. So these have to always have parentheses. Why? Because if you put a 3 in there, you get 0 in the denominator, the whole thing is undefined. Okay? So you're going to have brackets at 5 over 2 and negative 5 over 2. and parentheses at the 3's, because your answer cannot include 3 or negative 3. Now, so this is different from polynomial inequalities. In polynomial inequalities, if it's less than or greater than, it's parentheses. If it's less or equal or greater or equal, it's brackets. In rational inequality, if it's less than or greater than, it's parentheses, like polynomial. But if it's less or equal or greater or equal, brackets at whatever you get from the top, and parentheses at whatever you get from the bottom, because the bottom cannot equal 0. Okay? So 1, 2, 3, 4, and 5 intervals. I'm going to do the easy one since they alternate. 0. If you put a 0 in there, we need this to be less or equal 0 to be true, but we know it's positive because two negatives make a positive, so this is false. So that whole interval is false, then it's true, then false, so false, true, false. Intervals 2 and 4, which means -3, -5 over 2, including -5 over 2 and excluding -3. 4 is including 5 over 2 and not including 3. So this is my solution set right here. Okay? All right, 28. Page 316. So how do we solve the inequality? 1 over x plus 1 over x plus 1 is then 2 over x plus 2. Now it's rational inequality, so we need a 0 on this side. So we're going to move the 2 over x plus 2 over here, so it will be minus. And then you get this. So we have 0, but we need one fraction. There's 3 fractions. We're going to find the LCD, which is x plus 1 times x plus 2. So we're going to times the first fraction by x plus 1, x plus 2 to match the LCD, top and bottom. So we're going to get, so if we work out the top, it will be x squared plus 3x plus 2 over the LCD. Right, I foiled that. Now the second fraction is missing x and x plus 2. So x plus 2, if you distribute, it's going to be plus x squared 2x over the LCD. I just switched the order. And then the last one is missing x plus 1, x plus 1. So it's minus, distribute the 2x squared plus 2x over x plus 1, x plus 2, and this has to be less than 0. So now we have the same denominator, so we make it one fraction, put the LCD at the bottom, and then add and subtract the tops, x squared plus 3x plus 2 plus x squared plus 2x. Now this is the trouble right there. When you have a minus in front of a fraction, this minus goes every term on top, so it'd be minus 2x squared minus 2x. So we have 2x squared minus 2x squared, they cancel out. So we have 3x plus 2x minus 2x is just 3x, and then plus 2 all over the LCD. Now we're ready to do the critical values since we have one fraction and 0. So critical values, 3x plus 2 equals 0, x equals -2/3, and all this equals 0, x plus 1, x plus 2 equals 0, so x equals 0, that's a critical value, -1 and -2. So we have 4 critical values. And all of them appear one time, an odd number of times, so we can do the alternating method. So we have -infinity to infinity, 0 is right here, -2, -1, there's 2 critical values, and then 0 is a critical value, so we cannot use 0 as a test point, and then -2/3, which is right there. So and it's less than, so it's all parentheses at each critical value. So interval 1, 2, 3, 4, and then 5. and I cannot use 0 because it's a critical value, so I'll use 1, which is in interval 5, plug it in. I can plug it in there or in the original one. I'll just do all the way back. So 1 over 1 plus 1 over 2 is less than 2 over 3. So 1.5 is less than 2/3. That's no good, false. So 1 is in interval 5. Interval 5 is false. 4 is true. 3 is false. 2 is true. False. So the intervals are -2, -1, union -2, union -2/3, 0. Alright, so that is done. Now let's look at 38, page 316, and that would, I think, be the last one that I have to do in chapter 3. So it says find all values of x for which the graph of f lies above the graph of g. So f of x. So for the graph of f to lie above the graph of g, that means the y value of f has to be more than the y value of g. So 1 over x has to be greater than, that's what they mean by the graph of f lies above the graph of g. Like if this is f, this is g. So for each x, the y value of f has to be greater than the y value of g. F of x has to be greater than g of x. That's what we did, okay? So we're solving a rational inequality, so we want to set it equal 0, greater than 0, so we move that over. Then the LCD, so we're going to times this by x minus 1. So we have x minus 1 over x minus 1. We're going to times this by x. So we have x over x times x minus 1. And now we're going to write them as a single fraction. So it's x minus 1 minus x, which would be -1 over x minus 1 is greater than 0. Now, to find the critical values, there's nothing from the top, right? -1 cannot equal 0, so the bottom has to give me the work. So x times x minus 1 equals 0. So there's two critical values, 0 and 1. And again, 0 is a critical number, so we can't use it as a test value. 0, 1, infinity. So this is, and it's all parentheses because it's greater than. So we can use 2 from interval 3, and they will alternate because of what we said. So we're going to test 2 back into the original one right there. 1/2 is greater than 1 over 1. It's false because 1/2 is less than 1. So this is false, true, false. My solution set is anything between 0 and 1 is the solution. And you can graph it to see that the graph of f above the graph of g in that interval between 0 and 1. And that's it for 3.7, and all of chapter 3 is done.